Okay, so today we're going to keep talking about rotation. Okay, now the way that I like to think about rotation is to in a way that requires me to learn as few things as possible that are new. Okay, and this is what we like to do in physics often is take something new and describe it in terms of something we already know. So we're going to think about kinematics and energy today. And these are concepts we've already considered for translational motion, right? We have a coordinate we called x, which is an axis in a straight line, right? This is translational motion. Okay, and we have a coordinate x. Now what we're going to try to do is construct everything about rotation in terms of a coordinate we'll call theta, okay? And everywhere we have to do something for kinematics, for movement, for energy, we're going to try to do it in analogy to what we did in translational motion. So that the same equations and the same ideas and the same concepts apply and can be translated as much as possible. That way you don't have to learn as many new things, because in the end it really is very similar. Okay, it's just motion in a different kind of coordinate. Rotational motion, just think every time you see a theta, just think what it would be if it was an x. Okay, and so I'm going to step you through rotational kinematics, rotational energy, and we're always going to be translating back to translational motion, translational energy. Okay? Okay, so a couple of definitions, just to make sure we're all talking the same language. Right? We have a circle of radius r, right? And you have some angle theta. Then this distance along the circle we call s. Okay? And we usually work in radians, but of course one can work in degrees. Okay? So now if this is our coordinate, right? Then let's think what is velocity? All right, so over here we'll keep track of rotation. All right, so we have a coordinate x, which over here becomes theta. Okay? So what about velocity? Well, in this case, in translation, velocity is dx dt, right? Velocity is dx dt. Okay? So here, we're just going to translate that as directly as possible, right? And we'll say that velocity is the rate of change of this angle. Okay? It's the rate at which our coordinate is changing. All right, so omega is d theta dt, okay? So the velocity analog we call omega, angular velocity, is just d theta dt. Okay, so now imagine you are, a tiny little being living on a circular world where your coordinate is theta. Your velocity is how fast your theta is changing. All right, that's your motion around here. Okay, not terribly complicated. Now the only tricky bit about angular velocity is what is its direction? What is the direction of the angular velocity vector? Tangent to what?
To the circle at any x.
Yeah, so at any moment, your translational velocity is tangent, right? So this is v, right? That's your instantaneous translational velocity. That's the direction you are moving along a coordinate axis, right? But what about your angular velocity? What direction is your angular velocity pointing? Clockwise or counterclockwise, right? And so we need a way to represent that. A way to represent the direction of your angular velocity. And you can't have vectors which curve, right? Because vectors are defined just by their endpoint and their starting point. So we choose a sort of arbitrary definition, okay? So here I have to draw something in sort of 3D. If the motion is this direction, then we put the angular velocity vector up. Okay? So use your right hand. If the motion is in the direction of your fingers, the angular velocity vector goes in the direction of your thumb. If it's the other direction, then the angular velocity, I should do it like this so it looks more 3D, is down. Okay? So it's arbitrary, right? It's because we're dominated by right-handers. So we chose this arbitrary distinction. Thumbs up, huh? And we could have chosen an opposite, and physics would still work, right? So there's no fundamental reason. Don't stay up late at nights arguing with your friends about whether it should be up or down. It's just arbitrary. As long as we all use the same direction, we'll be fine. This is the one place where rotational motion really diverges from translational motion, because you don't have this problem in translational motion because you have linear axes. Okay, in this case, the axis the direction you're moving is sort of a loop. And so there are really only two directions, clockwise and counterclockwise. Okay. And we can't really point it along the direction, right? So we just point it up. Okay, so that's the direction of angular velocity, right? And in this case, the length of the vector is proportional to the magnitude of the angular velocity, right? So a long vector up means fast velocity, and a short vector means slow velocity, and a zero vector would be exactly at the origin pointing nowhere, right? So neither up nor down. So that sort of makes sense. Okay, and what about acceleration? Acceleration is just going to be the rate of change of velocity, right? Take the analog of translational motion. So this we call alpha. And here we did actually kind of a good job in trying to make an analog to translational motion, where we use A. Alpha is the omega dt. Okay, and what do we do with the vectors for alpha? Pointing to the center? Well, for translational, if you're moving in a circle, then your translational acceleration, right, is towards the center. You're right. The radial acceleration towards the center. But here we're considering the angular velocity, not the translational velocity of an object moving in a circle, but the rate of change of your angular velocity. So we use the same convention here, right? We can have positive alpha, we can have negative alpha. Okay, and you can think about these vectors the same way you think about normal vectors, right? If you have omega pointing up and you have alpha pointing up, then you have positive velocity and positive acceleration, right? So you have positive velocity and the rate of velocity is increasing. Okay, if you had, all right, here's your spinning. If you have positive angular velocity, but alpha points in the other direction, then it's the velocity is decreasing, right? And eventually velocity will go to zero. So just like in translational motion, if velocity and acceleration are pointing in the same direction, the magnitude of velocity is going to increase. If they're pointing in opposite directions, the magnitude of velocity will decrease until it gets to zero. And then it's going to go, the magnitude will increase again as the velocity gets negative. Okay, so you can use your intuition about the angular velocity and angular acceleration vectors like you used to use. Okay, and then the kinematics equations can be mapped exactly. Right? So where we had before velocity is equal to v0 plus at, now we have omega is equal to omega 0 plus alpha t. Right? So you can think about rotational kinematics the same way you thought about translational. You just write slightly different symbols for velocity and acceleration. Right? And where you had the most general equation was x0 plus v0t plus 1/2 at squared. Now you can write theta is theta 0 plus omega 0t plus 1/2 alpha t squared. Okay, so if you're given a problem that's like, you know, somebody starts out with this angular velocity and there's this angular acceleration, how long does it take to go a certain angle? You can use exactly the same equation to use for normal kinematics. Just translate everything from angular to rotation, from translational to rotational motion. Okay, those are the basic definitions. Is that a lot to absorb, or seems pretty straightforward? Am I actually on mute? And you've been standing here just talking like this the whole time? Okay. All right, well, since nobody likes to actually open their mouths, let's see if you can press clicker buttons instead. Yay! We only communicate electronically. You guys sit around with your friends and just text to each other rather than actually talking? What did he say? What are friends?
Yeah. What are friends?
Friends, what is this strange business you speak of? So, let's look at this question. It says, the graph shows angular velocity and acceleration versus time for a rotating body. At which of the following times is the rotation speeding up? So let's think about what's being shown. The axis is time. There are two things plotted. The green is the angular velocity, and the alpha is the angular acceleration. Right? So the question is, at which of the following times is the rotation speeding up at the greatest rate? Which you can interpret to mean the magnitude of the velocity is growing most quickly. Because if you have negative velocity and negative acceleration, that also means you're speeding up. Right? Remember, speed is the magnitude of velocity. So don't get confused about the signs. Okay, so how do we do this one? What is it asking us for? Yes.
So that would be then 1, 4, and 5.
Wait, speeding up at the greatest rate, right? So it can't be multiple answers.
When the magnitude of alpha is the greatest, so I mean, the slope is constant, so we see that like the slope is like, let's say, some generic number over 2, and when it hits 0, it goes 3 units to the right, and then usually the slope is 2, but that's the greatest magnitude.
So he's saying by symmetry, the magnitude of alpha is the same at 0 and 4, right? Even positive or negative doesn't matter. The magnitude is the same at 0 and 4, and therefore at 5 it's greater than it is at 4. So he's saying that alpha is the largest magnitude at time equals 5. Anybody disagree with that? Good. Okay, let's do another one. Here we have a DVD initially at rest, so that the line PQ on the disk surface is on the x-axis. Okay? The disk begins to turn with a constant alpha, so this is the angular acceleration, of 5 radians per second squared. At t equals 4 seconds, what's the angle between the line PQ and the x-axis? Okay, so how do we solve this?
Use a formula right here.
This formula, right? Okay, so what's theta? What's theta 0?
0.
What's omega 0?
0.
Okay, so 1/2 at squared, right? So you plug it in, and what'd you get?
A.
0.4 radians. Does anybody disagree with that? Anybody get a different answer? No? Nobody got a different answer? That's what I love, the clicker. Okay. All right, so let's put that away for a minute. Let's think about the connections between angular rotation and translational motion. Okay, I mapped to you the concepts, translation and rotation. So you can think about moving along a straight line versus changing your angle. Now let's see if you can think about the two at the same time. Because anytime you are moving in a circle, you also have translational velocities, right? Okay, so here we're moving in a circle. And we have our circle. We have a radius r, some angle theta, always from the positive x-axis. Okay, and we said earlier, and this quantity here is s. We said earlier that s is equal to r theta, right? So we can think about the motion, how far along the circle you moved if you moved a certain angle. Okay, so let's think about the velocity for s, ds dt, right, is r d theta dt. Well, what is d theta dt? Omega, right? And what is ds dt? It's just velocity, right? It's velocity along this circle. But it's a translational quantity. It's not an angular quantity. We're not measuring an angle. We're measuring the distance along a curved line, right? And we've done this before. Remember in other problems we had bent axes, just to make it more convenient to keep our signs straight. So this is velocity, is the relationship of velocity and angular velocity. And it makes sense, right? The faster your angle is changing, the more quickly you have to be moving along this circle, right? Or conversely, if you're moving along the circle really quickly, then your angle is going to be changing quickly. And the relationship between those is just r. Why is it r? Does it make sense that it goes like r?
Circumference is different due to r.
Sorry, the circumference is different?
Yeah.
Okay, but is this the right relationship? Why isn't it omega over r? Or r squared omega? Or log r? Why is it r? Jeffrey.
I'm not really sure if this counts as an argument, but so the circumference is 2 pi r.
Okay.
And 2 pi is equal for rotation. So if you wanted to measure the circumference of only this much, then you instead of 2 pi, you do it into that.
Exactly. Imagine two circles, right? If you're going to move one time around the smaller circle versus one time around the larger circle, you have a larger distance to travel in the larger circle, right? By how much? Well, by the ratio of the radii. Whereas the theta doesn't change. Theta has no information about how far out you are. So two particles with the same angular velocity will have a different linear velocity if they have different radii. And it's exactly because of the radius of the circle. That's a good physical way to think about it. An even lazier argument, a simpler argument, would just be by units. Right? You can't have log r or r squared or 1 over r, because then the units wouldn't work out. You're not talking about physical quantities anymore. Okay? This thing has to have units of distance. And so you have to have something over here with units of distance. This is per second. This is meters. This is meters per second. All right? It's as simple as that. And you'd be surprised how often we actually use this argument like in theoretical particle physics. You're like, well, what could the theory be? Well, there's only 10 possible theories you could write down because of dimensional arguments, so it has to be one of those. So let's just use all of them and see. I'm serious, we do that all the time. Okay, and similarly, it's very powerful, right, to think about the possible set of theories. Okay, and acceleration, right? The tangential acceleration, think carefully here, tangential acceleration, by which I mean acceleration tangent to the circle, right, because this is tangential velocity, is just dv dt, right? Now r doesn't change, so this is just d omega dt, and what's d omega dt? Alpha, right? So the relationship between tangential velocity, that is velocity of your motion around the circle, along the circle, is related to the acceleration of your angle, again, by r, for the same reason. So fortunately, the two universes are simply connected. Now remember, the radial acceleration is v squared over r, right? This is radial acceleration. This is the acceleration necessary to move in a circle. And this we could, if we wanted to, rewrite as omega squared r, just by using this relationship. We're not deriving anything new here, we're just writing it in terms of something else. Sometime you might get a problem where you're given the angular velocity instead of the linear velocity. It might be more convenient to think about it in these terms. Then again, if you're given the angular velocity and you need a linear velocity, you can always just translate it using the radius and then plug it in. No great insights here, okay? Okay. All right. So I got another couple of these for you. Help you think about how this works. Okay. First I want to show you this because there's no chance I could draw this accurately on the board. So, let's see. Full screen. Okay. So when you're thinking about something moving in a circle, we were talking about tangential velocity and tangential acceleration and radial acceleration. Remember, radial acceleration is what you need to move in a circle. Tangential acceleration is acceleration along that circle. Now, something can have both tangential and radial acceleration, right? That means it's not moving in a perfect circle, okay? But any motion can be broken up into these two quantities: acceleration of radial acceleration with respect to some origin, some axis of motion, and tangential acceleration. And you're just breaking these things up into two orthogonal vectors, right, where the total acceleration is just the vector sum of the two. So for example, here this problem says, given omega and alpha, which are the angular velocity and acceleration, find the components, the tangential, radial, and total acceleration. All right, well this isn't hard. It's just remembering that the tangential acceleration is just the radius times the angular velocity, angular acceleration, which we were given, and the radial component is omega squared r. Right, this is what you need to move in a circle, plus you have this. If you want to combine the two together, you just add them in quadrature. Nothing wrong. Okay, but this is what I actually wanted to show you. Back to our DVD. This one's going crazy and rotating with ever-increasing speed. The question is, how do the radial acceleration, the centripetal acceleration, and the tangential acceleration, A tan, compare at points P and Q? So you have the same DVD, which means points P and Q are going to have the same angle, the same angular velocity, and the same angular acceleration, because they're hooked together, right? They're always going to have the same angle. But they have different radii. So this question really is about the radial dependence of the tangential acceleration and the radial acceleration. Okay, so no consensus here. Why don't you discuss with your neighbor and vote again and see if we can converge. All right, you guys are not very persuasive. Okay, so we're being asked about the radial acceleration versus the tangential acceleration for points P and Q, right? Now, do P and Q have the same alpha?
Yes.
Why is that?
Yes.
Yes or no?
Yes.
Why yes?
Because they have the same speed.
They have the same angular speed, so therefore they have the same angular acceleration. Because they're connected, right? They're on a disk together.
Yeah.
And so their angles are the same no matter what happens, unless you're breaking the disk. Okay, so the same alpha, right? What about the radius? Different radius, right? Q is a larger radius. Okay, so who thinks the answer is D? A lot of people voted for D. Why D?
The angle is staying the same, and the radius is different. So, I just think that on a merry-go-round, your tangential speed, so how fast the course is going to be around, it has to be faster on the outside, so you can keep up.
Yes?
Is that
Okay, so as you go further out, your tangential velocity, tangential acceleration is larger, you're saying. And that's true. And here we see the dependence of the tangential acceleration on r confirms it, right? It's r alpha. So a larger r means a larger tangential acceleration. Okay? What about the radial acceleration? It's the same r dependence, right? Why? Well, first of all, because it's written here on the board, right behind me, right? But also, you see, if you fix the angular velocity, if you have the same angular velocity, then the only difference is r, then you're going to have a larger radial acceleration if you have a larger r. Now you might think, well, I was thinking about in this case, what if I try to use this equation? Well, that's fine, but do they have the same v squared? They don't have the same v squared, right? Being on the same disk doesn't mean they have the same tangential velocity. It means they have the same angular velocity, right? Which means the rest of the dependence is on r. Questions? Okay. All right. Here's a tricky one. How does the speed of the gears, so here we have two gears connected by a chain, right? In the last example, we've had two gears, we had basically 2 points which were on the same disk. Here we have two disks, but they're connected by a chain. Think about what that means if they're connected by the chain. The same tangential velocity, right? That's what the chain does. That's its job. Okay? So if they have the same tangential velocity, what's the relationship between their angular velocity, given that they have different number of teeth on them? It's the basic principle of a bicycle, right? All right? This looks like the distribution we get when nobody has any idea what they're doing. All right? Most people just press A. So, how do we approach this problem?
We can set their tangential velocity.
Okay. So I'll say velocity of the rear is equal to velocity of the front. What does that get me?
Solve for their independent alphas. Because
Alphas? You mean omegas?
Yeah,
Okay. So here I have, what's the relationship? Well, I can say R rear omega rear is R front omega front, right? And then I can get the ratio, for example. Front over omega rear. Did I get that right? So the radius is an inverse relationship to the angular velocity. Does that make sense to us? Right? Same linear velocity. If you have a huge wheel, it's going to be spinning more slowly, right? And that's the whole idea on the bicycle. You spin the small wheel around your pedals quickly, and the big wheel doesn't have to move that fast. The big wheel of the actual wheel touching the ground doesn't have to move that fast. Okay, but this asks us to relate it to the number of teeth, right? Not to the radius. What's the relationship between the radius of the wheel and the number of teeth? What's that?
by the length of the circumference of the circle.
Uh-huh. The spacing is assumed to be the same. Why is that?
Because we assume that.
Well, would your chain work if the spacing was different in the front and the back? No, right? That would be a really, really bizarre chain. I guess you could have like a dual chain. Right? You're just designing that in your head right now? Awesome. Sorry? Yeah, so you have to assume that the spacing is the same, right? For the chain in the front and the back. Okay, So you say
You just have like this.
2 pi r front over the number of teeth in the front is 2 pi r rear over the number of teeth in the rear, right? The spacings, this means the spacings are the same. You get some frowns. Okay, and this gives me a relationship between the number of teeth and r, which is what I want, right? The pi's cancel. Right, and so then I can say r rear over r front is equal to n front over n rear. Is that right? R rear. No, this is not F. No, F, F, R, R. Yes, thank you. R, R, F, F. Yes, that looks right. Okay. And so then you combine these two sets of equations to give you a relationship between the omegas and the r's, which tells you n front over n rear over n front is omega front over omega rear. So as usual, the hard part in a physics problem is taking the physical situation and translating it into the equations we already know. Once you have a couple of equations written down, the rest is just simple algebra. But here the trick was understanding that having a chain connecting the two wheels meant same tangential velocity, not same angular velocity, and that the gears had to have the same spacing of teeth because they have a single chain. Okay, do another one. Okay, compared to the tooth on the rear gear of the bicycle, a tooth on the front gear has what in terms of linear speed and angular speed? All right, so discuss with your neighbors. Change your votes if you need to. Okay, let's shut it down. Everybody put your final vote in.
100%.
We get 100%.
You can't tell people what to think, man. All right, but if you're pressing B or C, I want to hear why in a moment. Okay, so how do we solve this one? Well, we're being asked about the linear speed and the angular speed, so let's take it one at a time. Do they have the same linear speed or different linear speeds? Same. We just talked about that for 5 minutes, right? The same problem a minute ago, the chain and force is having the same linear speed, right? Unless the chain is stretching weird. So it has to be the same linear speed. That means it's B or D, or perhaps still E, but it can't be A or C. What about the angular speed? Why is it slower? What's the relationship between linear velocity and angular velocity? V is omega r, right? So same linear velocity, a larger radius, you have to have a smaller omega to compensate. And that's, again, the basic principle of the bicycle. Right? If the gear that you were pedaling, it was the same size as your back wheel, would there be any point to having a gear? Not at all, right? Okay, questions about that? Okay, so the point of that was to think about rotation, the rotational inertia. Right? So we thought about rotational velocity and rotational motion and rotational acceleration. Now let's think about rotational inertia. And rotational energy. So say you have some object that's rotating, right? Give me an object.
Fat CIA agent.
A what?
A fat CIA agent.
A fat CIA agent. All right, there's something else.
An elephant's tail.
Elephant.
An elephant's tail. Something else. And a new idea. Come on, guys.
A galaxy.
A galaxy? A what? A juice box on a stick? How about 2 little girls on a stick? How about that?
Yeah.
Okay. Okay, just 1 little girl on a stick. How about that? Okay? Say you have a little girl, right? No little girls were actually hurt in this demonstration, okay? Little girl, and she's spinning around. Okay. Let's think about how she's spinning around, right? Let's think about the energy of this motion. Now, I don't know how to think about a little girl spinning, so I'll say, let's think about this little girl in terms of the little particle she's made out of, right? So there's a little particle with some radius, another particle with another radius, right? And any system, little girls, elephants, CIA agents, whatever, can be thought of as a sum of little particles, each with their own radius, right? So what is the kinetic energy of this little girl in terms of the particles that she's made out of? Well, the kinetic energy is just 1/2 m1 v1 squared plus 1/2 m2 v2 squared, right, plus whatever, summed over all of the particles that make up the little girl, or whatever it is you're sticking on a spit and roasting. But you can translate this into kinematic quantities. Did I say roasting?
Yeah.
You guys are sick. I totally didn't say roasting. Okay, but let's translate this into rotational quantities, right? So we have m1, and then we have r1 squared omega 1 squared, right? Because v is omega r, so v squared is omega squared r squared. See what I did there? Plus 1/2 m2 r2 squared omega 2 squared plus whatever, right? So I just translated it to a different variable, which we already know. Now, their masses of these two particles are going to be different, right? Their radii are going to be different. What about their angular velocities? The same, right? As long as the little girl is strong and rigid as she's rotating, then she's going to have the same velocity, right? So I can say, well, that's just a single velocity there, and then I can write this as 1/2 m1 r1 squared plus m2 r2 squared plus omega squared, right? Is the kinetic energy. Now remember, we like to think about every quantity in rotational terms as an analog to translational terms. And in kinetic energy, we have 1/2 mass times linear velocity. Right, so here we have rotational velocity, so we're close, right? We have 1/2 something times rotational velocity squared. So if we could identify this as some sort of rotational inertia, the way mass is translational inertia, then we'll be home free. And in fact, that's just what we do. We call this I, where of course I is m1 r1 squared plus m2 r2 squared plus, all right, so your rotational inertia is constructed just by analogy to translational inertia. Mass is the thing that makes it hard to speed you up or slow you down. This quantity I, which we call moment of inertia, which I prefer to think of as rotational inertia, is m1 r1 squared, etc. And what the little girls in the video were showing us is this doesn't just depend on the masses, it depends on the radius. A large radius means a larger moment of inertia than a smaller radius. It's harder to spin that stick if the juice boxes are far from the center because they have a larger r. So it has a larger moment of inertia, and therefore it's more difficult to give it rotational velocity or rotational acceleration. Just the same way something with large mass is hard to give velocity or acceleration or to decrease it, right? Okay? Now the interesting thing about moment of inertia, one way that it's different from translational inertia, or just mass, is that it's defined with respect to an axis. Right? Mass is not. Mass is just a property of an object. Doesn't matter what direction it's moving or how you're looking at it or how you define your axes. But the moment of inertia does depend on that. Say, for example, here we have a disk, okay, and disk A, and then it's connected by a rod to a disk like this. Okay, and then this is connected by a rod to another disk in the same direction. Okay. The moment of inertia of this horrible thing, right? This comes like here. Okay. The moment of inertia of this thing depends on the axis, right? So for example, if, let's use different colors to differentiate. If you choose an axis through the center of A, right, if this is your axis, and imagine these things have very small radii here, so we can ignore the moment of inertia of A itself around A. Then the moment of inertia around the axis A is just NB times RB squared plus MC plus times RC squared. This is assuming that radius A is very small. Okay, so if you try to rotate this thing through here, then it's going to be dominated by these two masses, right? Whereas if instead you had chosen to rotate it through here, call this B and C, then it would be essentially just determined by A, right? So the axis you choose makes a difference in the moment of inertia. And that makes sense. Rotating something in one direction doesn't make it, can be easier or harder than rotating in another direction. Okay? And the more general expression, we wrote it here as a sum if you have things that are made of particles, but of course many objects in the world are not made of tiny discrete particles which you can separate and measure, so the more general expression involves an integral over the density. Okay? So it's a volume integral, dV, of the density as a function of r times r squared. Okay, what does dV mean here? For those of you who haven't taken vector calculus yet. Okay, so it's a three-dimensional integral, dx, dy, dz, of the density, right? This is the analogy to mass here. So the moment of inertia should depend on the mass and on the radius squared. So this is basically like infinitesimal piece of mass times the radius of each of those pieces of mass. And we're not going to do a lot of these calculations, don't worry. But I just wanted you to think about that in your head, play with it, rotate it around, the joke, and think about how that is the generalization of this. Questions about that?
Where did inertia come from? Like, how do you just sub it in for ml squared?
It came from here. It came from saying that I wanted the kinetic energy to be an analog to the translation kinetic energy. So I wanted 1/2 some inertial quantity times velocity squared. And so I said I have the 1/2, I have the velocity squared, so I'll associate this with rotational inertia. It came really from just trying to construct quantities in analogy to translational motion. Plus it makes intuitive sense. Things which with large I are harder to rotate. Okay, and in your book you will find the moment of inertia of many typical objects. So you don't have to do these kinds of integrals very much. For example, if you have a rod and you rotate it around the center of the rod, then the moment of inertia is I equals 1/12 ml squared, where this is a rod of length L. Okay? And if you have a sphere and you rotate it around the center of the sphere, the moment of inertia is 2/5 mr squared. Okay, in the book I think there's a whole table. And this is not something you should bother memorizing. Nobody needs to know these things off the top of their head. If you ever need to know this for a problem on an exam, I'm going to give it to you because I don't think it's worth your while. To memorize, but what you should do is understand the dependence on the mass distribution. So for example, a sphere of mass m, what's the relationship between that and a thin-walled hollow sphere, right? So imagine all the mass is distributed at the radius, right? So you're still rotating, you still have the same mass, you're still running around the same axis. Is this thing going to have a larger or a smaller moment of inertia than the solid sphere of the same mass? Why larger?
Because the mass is farther from the center.
Yeah. If you move the mass farther from the center, you're increasing the r squared, right? You move the juice boxes out, it's harder to spin, right? And if you look it up, this guy has, this is 2/3 mr squared. Okay, so you should understand in general the relation. You should be able to guess in general the relationship between the moments of inertia of two different objects, just based on these arguments of how far is the mass in general distributed from the axis of rotation. Okay, questions about that? Okay, so let's practice that one. All right, so here's a picture of a lot of them that are in your book. Is it just me or is that projector seems dim today?
It changes.
Yeah. Okay, so you have a flat object, you have a flat object with a thickness, you have a rectangle, you have a slender rod rotating through the center versus rotating through one end, hollow cylinder, solid cylinder, thin-walled cylinder, etc., etc. Okay, so these are a bunch of examples. And again, don't memorize them, but take a look at them and make sure you understand roughly what the dependence, the relationship between them. Okay, so here, three objects here have the same mass and the same radius. Each object is rotating about the axis of symmetry, shown in blue there. All of them have the same rotational kinetic energy. All right, which one is rotating the fastest? Now remember, we said this is rotational kinetic energy here. 1/2 I omega squared. So they have the same rotational kinetic energy. They have the same product of I omega squared. Which one is rotating the fastest? Yeah, this should be solid cylinder. Yeah, sphere. Sorry. Everywhere it says sphere there, it should say cylinder. I hope that's obvious. Okay, we have a lot of answers. So how do we figure this one out? What's our handle on it? Yes?
You could, since they all have the same kinetic energy, you can just set them all equal to each other, plug in the i's, and see which one would have the depend on the lowest mass at that point.
The lowest mass?
Or,
Well, we're being asked about the angular, we're being asked which one is rotating fastest. So we're being asked which is the largest omega, right? So you're saying the same kinetic energy, the larger omega is going to come from a smaller I, right?
wouldn't it still have the lowest mass?
Well, they all have the same mass.
Oh, okay.
They have the same mass and the same external radius. Right? So if they have the same kinetic energy, then the largest omega is going to come from the one with the smallest I, right? For the same amount of energy, you get the most spin out of something with the smallest amount of rotational inertia. And which one has the smallest I? Well, it's the solid cylinder because it has more of its mass close to the axis of rotation, which is small r, so that makes sense. Plus, it's given to you right here. You can compare these guys. This one is obviously the smallest number. Right? Questions? Okay, let's do another one. You have a rotating solid sphere and you want to double its radius while keeping its kinetic energy constant and keeping its mass constant. To do this, the final angular velocity has to have what relationship to the initial angular velocity? Right, so kinetic energy is constant, right? This is 1/2 I omega squared, which is equal to 1/2 I So the kinetic energy is 1/2 I omega squared, right? In this case, I is 5/2 mr squared, right? That doesn't really matter because it's the same dependence for both cases. So you can plug that in and say that just goes in here, right? And you have mr squared omega squared. The final kinetic energy is going to be the same quantity, but you're changing the radius, right? And so the question is, what does this have to be to give you the same kinetic energy? So if you double the radius, this goes to 4, right? But it also has dependence on omega squared. So the ratio of omega squareds is 4, which means the ratio of omegas is 2. Questions about that? No? Okay. Okay, let's do an energy example problem. Okay, here we have a 50-gram pulley is rotated by pulling a rope with force 9 newtons for 2 meters. So we have a pulley which weighs 50 kilograms and has a height of 0.12 meters. There's a rope attached to it. And the rope is pulled by 2 meters, and the force is 9 newtons. Okay? And so the question is, a 50-kilogram pulley is rotated by pulling a rope with force 9 newtons for 2 meters. What is the final rotational speed of the pulley? So when you pull on the rope, what do you do? You're spinning it, right? You're putting energy into the system, right? You're doing work on the system. How much work are we doing? Right? You apply a force over a certain distance, that's work. Very easy to calculate, it's just the product of the two. Where is this work going to go? It's going to go into kinetic energy of rotation of the pulley, right? Nowhere else for it to go. How do you write that? Well, that's 1/2 I omega squared. Right? This is the kinetic energy of rotation. Just like kinetic energy of translation is 1/2 mv squared, here we have rotation is 1/2 I omega squared. Right? Rotational mass, rotational velocity. Okay, and if we look up what I is for this kind of thing, 1/2 mr squared. Okay, we can just plug that in here. right? So then we can just solve. Now we have, so we turned work into kinetic energy. Kinetic energy is a simple relationship to velocity, which is what we want, right? So we can just solve for for F delta x over m r squared, right? And these are all numbers that I've been given. I've been given the mass. I can get the radius from the diameter. I've been given delta x. I've been given the force. I know the number 4, right? And so this tells me the answer is just, anyway, you can just plug it in, okay? So here's an example of translating work, linear energy, into rotational energy. So far, when we've been doing these kinds of problems with energy, we've been thinking about potential energy and kinetic energy of motion. Now we're going to add one more element to some of these problems, which is rotational energy of some of these objects. Okay, so let's do another example before we run out of time. Here we have a falling block tied to a string, wrapped around a pulley which rotates. Okay, previously our pulleys haven't been rotating, and so we didn't have to think about their rotational energy, right? Because the pulleys just slid, the ropes just slid over the pulleys. But now we have a block tied to a string wrapped around a pulley which rotates. The question is, how quickly is the block falling and how quickly is the pulley rotating just before the block hits the ground? Okay, so the block is some height above the ground, right? And the question is, what is the speed of the block when it hits the ground, and what is the rotational velocity of the pulley just before the block hits the ground? Now previously, if we had a simpler problem, when this is a block falling, we would translate the potential energy of this block into its kinetic energy, we'd be done, right? Very simple. But now we have something else going on. This potential energy, initial potential energy, which is mgh, is getting turned into 1/2 mv squared of this block, sure, but it's also getting put into 1/2 I omega squared of the pulley, right? So the block will be going slower because some of the potential energy is turned into rotation of the pulley. It'll be going slower than it would have been without the pulley, right? The pulley is slowing it down just by stealing some of the potential energy for its own rotational kinetic energy. Okay, so it has to share. Now this seems complicated because now we have more stuff, right? This is a different velocity, what is this guy? But we have a relationship between this translational velocity, this tangential velocity, and this omega. So we can always remove one of these variables, right? And I, in this case, is 1/2 mr squared, right? And we can replace this with v over r, right? Because the pulley the rope is attached to the pulley, so the rotational speed of the outside of the pulley is the same as the translational velocity, the tangential velocity of the rope. All right, so we can connect these two. And what would happen if this wasn't the case, right? If the rope was not attached to the pulley. The pulley wouldn't spin, and we wouldn't even have this term, right? So the fact that it's attached to the pulley makes it more complicated, but then it also makes it simple because we know something about the relationship of the rope to the rotational speed of the pulley. Okay? And so now if we're given the mass, then we know the height, right? We can solve for everything to get the velocity of this guy in terms of just these masses. And then we can translate that to the angular velocity, which is what we were asked for. Okay, let's just do one more quick one before we go. An example of using center of mass together with rotation. Okay, we have a meter stick with a mass of 0.616 kilograms, pivoted around one end so it can rotate without friction along a horizontal axis. Okay? So it starts off horizontal, and then it swings down here. The meter stick is released from our horizontal position. First it asks us, A, find the change in gravitational energy. Change in gravitational energy. So that seems kind of yucky, right? Because this guy goes, I mean, we know the length of this thing, right? It's a 1 meter, meter stick. 1 meter, right? And the mass is 0.16 kilogram. Some tiny little piece of this guy has a large change of gravitational energy because mgh is large. This guy over here has no change at all. So how do we do this? Do we have to do some like ugly integral? No, we could just think about the center of mass, right? Center of mass is this guy is in its center. Center of mass over here is in its center. So we can replace this complex shape with just a simple effective particle which acts the same way. So the change in gravitational energy, right, is just mg times the the height of the center of mass, initial minus the height of the center of mass final, right? Which in this case is 0.5 meter. Okay, and then they say, find the angular speed of the stick. Well, the change, so we have initial energy, initially we have potential energy, and finally we have potential energy plus kinetic energy of rotation, right? We already know what this is, we just calculated it, the difference between these two potential energies, right? And in fact we could set this one to be 0 to make this one simple. So mg times 0.5 meter is equal to I omega squared, right? So here the gravitational potential energy gets turned into rotational kinetic energy, and we're asked to find the angular speed, right, which is just omega. So it's just like those problems of a block falling where you turn the potential energy into kinetic energy to find its velocity. Here we're turning potential energy into rotational kinetic energy to find rotational velocity. Exactly the same kind of problem, just translated into rotational terms. Okay? And in the examples, in the lecture notes, I have 3 or 4 more similar examples we can look at. Okay? That's all we have time for today.